So I'm going to today talk about separable metric structures, continuous logic. I don't expect you to know anything about that, so I'm going to start today with the basics. I'm going to first do the semantics and then do the syntax, because I feel like it turns out to be more understandable that way. So we're going to start with metric structures, and the idea is we're going to take models and think about continuous analogs of everything. So a lot of continuous logic is sort of done by analogy, and if you keep that in mind, it's hopefully a little bit easier.
Last question.
Yes.
We actually have had some exposure to continuous logic because Persigo was a student here.
Okay.
Also because I'm here.
I've noticed in the literature there's sort of 4 or 5 different ways of doing it. Does
Yes.
it make any difference?
I think no, but you do have to translate. If it matters, I'm following model theory for metric structures, the 4-person monograph. I think that that's sort of the best place to see a treatment that is complete. I think different people treat different things, and sometimes you have to be careful about the notions they're using. Something that I have a big pet peeve about, particularly in the infinitary setting, is using the logical and the logical or for max and min, and 50% of the time I disagree with what's happening. So not really. Hopefully today I can give you at least a treatment that you can use. Okay, so for a metric structure, what I really mean is I'm going to take a complete bounded metric space and treat it like a set on a model. So a model is a set plus constants, functions, and relations. So a metric structure is a complete bounded metric space. The boundedness you can do away with if you do one of the many tricks on the literature. And we have an interpretation of some constants. Now, I have functions from some Cartesian power of the model back to the model. The difference is I'm going to ask that they be uniformly continuous. And later in the syntax, I'm going to actually ask that the syntax tells me the modulus of continuity. I know how uniformly continuous it is. And instead of predicates, if you think of a predicate as, a function to 0, 1, then now we're going to the interval. So it's some uniformly continuous function from some Cartesian power to the model to, in this case, some closed interval of the reals. Sometimes you do everything with 0, 1. That doesn't really matter for the stuff I'm doing. I want to allow any closed interval, but always a closed interval. So, and we say that my metric structure is separable if my metric space is separable and my interpretation is countable. So you could in some way say that's separable, but let's keep it easy and just say I have countable many functions, predicates, and constants. So let me give you some examples. The first one is the trivial one. I'm going to take a model. I'm going to put the discrete distance on it. If 2 things are equal, their distance is 0. If they're different, their distance is 1. And turns out that anything is uniformly continuous with respect to that distance. So voila, I've made a metric structure. But that isn't super helpful, sort of thinking how they look. So let me give you another example. I can take Cantor or Baire space, 2 to the omega and omega to the omega, and I can put a neat distance on it. If I have 2 sequences, if they're equal, their distance is 0. If they're different, look at the least bit where the distance where they're different. The distance is 2 to the negative n. And if you want to see a function, we can put in the left shift. So yeah, just the left shift. Hopefully, I don't need to explain more than that. Look, I was doing this last night. I was like, it's the left shift of the right shift. So I have to kind of do it with my hands to remind myself. More examples. Hopefully this gets us thinking. So take a probability algebra. So I have a space, I have a measure on it. The measure of the whole space is 1. I have a bottom element, a top element, and I have sort of an algebra of sets on it. I can create a distance. We're saying the distance between two elements of this probability measure is the measure of their symmetric difference. And okay, this probably takes a little bit of probability theory, but that is a complete bounded distance. And so I get a metric structure where 0 and 1 are constants, the complement, meet, and join are functions, and I'll throw in the measure just to have a predicate, just to give you an idea of what these things can look like. The last example is I can take Hilbert space or any Banach space. Okay, that isn't bounded, so what are we gonna do? You could do two things. You could say I'm just gonna take the unit ball and take restricted addition and restricted multiplication by, I guess I want I'm talking about countable structure or separable structures. So by rationals of norm less than 1, or you can do this weird thing. Maybe you've seen this before, where you go, okay, here's the 0, and I'm gonna make countably many sorts, right? One for the ball of radius n for every n, and I add functions that tell you how to go from each ball to each ball, and I have these countably many sorts, and there are countably many additions. You have an addition function that goes from the ball of radius n cross the ball of radius n to the ball of radius 2n, so on and so forth. Either or, but
So just Brett
yeah.
Hart had a student who in his PhD had a better way of doing this. But I forgot. I mean, but anyway, I shouldn't be saying that was some nice thing because this leads to all sorts of irritating problems. So definability is horrible and things like that.
Yeah. So again, boundedness is optional, but now you're dealing with this nightmare. But anyways, we can put Banach spaces. The norm is a predicate. Addition and scalar multiplication are functions, etc., etc. So okay, hopefully that gives you an idea of how metric structures look like. Any questions before I move on? Okay. So let me start by if you've never heard about Scott analysis, I'm going to sort of start this with a paper by Itai Ben-Yaakov, Michael Ducha, Andrei Nies, Todor Sankov, which is called metric Scott analysis. And among the many things that they get in that paper is this sort of Scott sentence result, which says, hey, if I have a separable metric structure in a language in continuous infinitary logic, I'll tell you the syntax eventually, I promise. Turns out that continuous infinitary logic is sort of strong enough to classify separable structures up to isomorphism. So I find the sentence that if I take every other separable structure in the same language, the sentence is 0 exactly when the two models are isomorphic. And this is, again, an extension by analogy of an old resort of Dana Scott for countable structures in just infinitary logic that you've probably seen before. So let me just kind of start with the punchline of kind of the things that I want to talk about today. Maybe I'll get there, maybe I won't, we'll see. Suppose I give you a separable metric structure and some finite tuple. And the following are true. The metric closure of its automorphism orbit, wherever I can send it by automorphism, is definable in continuous infinitary logic without parameters. With parameters, it'll probably be easy, but I don't need parameters. I can somehow tell you where they can go. Now, if you know the automorphism orbit of any tuple, turns out that basically everything that could be definable is definable. i.e., the definable sets of a separable metric structure are exactly those that are metric closed and automorphism invariant. You should know that definable sets are automorphism invariant. I'll talk about why I can only define metric closed things when I get there. And also, a little bit going back to what we just saw, it turns out that this Scott sentence, whatever it is, you can take these definitions for automorphism orbits and put them together to get the Scott sentence. So there's this weird sort of inside-outside principle. Once I fully understand how automorphisms work inside my structure, I can classify it amongst all the separate ones. Yes.
Is an automorphism what I think?
Yes, so the constants remain the same. The values of the predicates are the same. If you ask something like for a function, the distance between two things and their images is the same. So everything should be preserved. In particular, it's an isometry, etc., etc., etc.
So in particular, what Banach space people call isomorphism does not count.
Yeah.
It has to be isometric.
Yes.
Okay.
So if you think about it as a logician, yes. If you think about it as an analyst, no.
Well, unless you're operator algebra.
Yes, because in sister algebras, they're all isometries. Any other questions?
So you're
Yes.
saying that for any of the one.
So for any tuple, if I give you a tuple, the set of all things that are images under automorphism, if you take the metric closure of that, that's the final.
But I think question was for you don't fix automorphism. You just look at the
Yeah, it's over all automorphisms. Yeah. In particular, one thing to say, whenever I talk about definability, I always talk about metric closed sets. If I don't say the word metric closed, please add it in post. It should always be there. Any other questions? Okay. So the starting point is again by analogy. So let's forget about continuous logic for a second and let's look at what's happening for just countable structures in infinitary logic. So first of all, what is infinitary logic? Take your classical first order logic and you're gonna add countable disjunctions and countable conjunctions. So just to give an example, a typical first order structure for first order sentences, for example, my set, I have exactly 10 elements. So there exists x1 up through, well, I'm going to say xn, such that for every y, all the xi's are different. And y is equal to one of them. Oof. Right? So this is a fair thing in just first order logic, but now I can take the countable disjunction of all of these things. And suddenly I've written a statement that says I'm finite. Okay? Now, for this stuff I'm going to talk about, I want to talk about how to count quantifier complexity. So the way that I'm going to do it is I'm going to count the quantifier alternations, and I'm going to treat countable disjunctions as existentials and countable conjunctions as universals. So this is quantifier free. This is a universal. For universals, we use pi. So I'm going to say this is a pi1 infinitary formula. So that makes each of these sigma 2. This is not an alternation, right? So this whole thing is sigma 2 infinitary. So if you want the sort of whole definition, because it will show up in the slide, the sigma 0 infinitaries are the pi 0 infinitary formulas. They're the quantifier free ones. And we say that a formula phi is sigma alpha infinitary if it is of the form a countable disjunction of existentials. The existentials might have different lengths for each of formulas such that each psi n is pi alpha, pi beta for some beta less than alpha, though the beta may vary over formulas. So you could have like say a sigma omega formula could be the disjunction of a sigma 1, a sigma 2, a sigma 3, a sigma 4, so on and so on. And it's pi alpha if the same thing is true, but you flip all the quantifiers. Okay? Are we good with this? Awesome. So in the countable structure world, there's been a variety of definitions of Scott rank using original ideas of Scott. I guess one of my the professors at Berkeley when I was a PhD student there, Antonio Montalban, in 2015, got angry and said, I have a better definition. So we're gonna say that if I give you a countable structure, the Scott rank of that structure is gonna be the least ordinal alpha, such that all the following conditions hold. Every automorphism. Hello? Sorry, I did click next, but it's not showing up here. Sorry.
So should we call the tech support?
Yes, if somebody could, because I don't know what is happening.
So it's on the computer, but it's not on the.
Oh,
Oh, there it is.
yeah, there's a lag.
Oh.
Let's put it that way.
Okay, Chrissy looks like it's showing up fine.
Showing up fine on Zoom.
Okay.
So it's an internal lag.
Yeah.
Well, give me 1 second. I'm gonna try something. This seems okay. If I do this, if I do that, no, because my computer is a slide ahead.
No.
So something is going wrong and I don't know where it is. Let me try this. I don't know what's going on. Let me see.
So IN is same as INF. You hit INF on Blackboard, now it's IN.
Oh, did I put, why did I do inf? It should just be in. Okay.
I think I prefer it.
Yeah, inf makes sense.
Yeah.
Suggestive.
Huh. Can someone please call the tech support guy? I don't know what's happening.
Oh, it's showing, number 2 is showing up now.
Yeah, okay. So while you go, let me get through this slide. Okay. So first of all, the automorphism orbit of any tuple is definable, and it's definable by a sigma and alpha formula. So I can define all the automorphism orbits. If you remember what I said earlier, you should see where the analogy is going. Hey. Okay. So we're back. So I can define every single automorphism orbit by a sigma alpha formula. The formula is different, but they all satisfy this complexity. The Scott sentence of A, so essentially the same thing we talked earlier. There is a sentence that characterizes this structure from up to isomorphism among all the countable structures on the same language, and that sentence happens to be pi alpha plus 1. And then this typomeeting Rilnijevsky statement, which says if I have a pi alpha type that is realized in A, then there is a sigma alpha formula that isolates it. Because these aren't complete types, I can't really talk about isolation in the same way, but it's the same idea. There is a sigma alpha formula such that the model thinks that that there is somebody that realizes that formula, and the model also thinks that everyone who thinks that formula is true realizes the type.
Can you just see what exactly do you mean by pi alpha type?
A type made out of pi alpha formulas. Partial type doesn't need to be complete. But if you read that, that's essentially the same as isolation, except I need a definition that works in partial types. And so the question that I sort of did for my thesis a lot is, can I get a robust Scott rank for separable metric structures? Essentially, can you get a statement like this to work? Part of the problem is we first need to talk about quantifier complexity for formulas in continuous logic. There are some questions to ask, but this is the end goal and it's still out of reach.
But sorry to interrupt
yes.
again, so isolation, they're just call it by implication. So there are possibly things which realize the type but don't satisfy.
Yeah.
But that's okay.
That's okay because this type is partial. Okay. So now let's do the syntax. There are multiple ways of doing the syntax. This is the way I'm going to do it today. So formulas are really functions from some condition power of the model. If you have sorts, you have to pick sorts, but let's forget about sorts. To some closed interval of the structure. The language itself tells you which closed interval you fall into and tells you how uniformly continuous you are because it has a modulus of continuity. If you don't know what a modulus of continuity is, it's a function delta that goes from 0 to infinity, open, if it's for an n-ary formula n to 0 infinity, it satisfies some nice properties. Delta of the tuple of all zeros is 0. It's subadditive and non-decreasing. So delta of little delta is less than or equal to delta of little delta plus delta prime, less than or equal to doing delta separately of each. It is continuous. And we say a function f from a metric space X, so Cartesian power to Y, respects delta if the distance in Y between f of X and f of Z is less than or equal to delta of the individual distances. So distance in X of x1, z1, all the way up to the distance in X of xn, zn. Okay, so this gives you a way to find deltas out of epsilons. And if you have a module, if you respect the modulus of continuity, you're uniformly continuous. So the way that works is my language gives me modulus of continuity for all the basic symbols. And once you know those, you can construct them for any formula. Okay, how do we put formulas together? If I have two formulas phi and psi, I'm going to allow the following connectives. I can add them. I can take max. I can take min. I can multiply them by rationals, including negative numbers. And I'm going to add the function that's constant 1. It's really a function from nowhere. It's always 1. If you've seen continuous logic before, you could say, hey, I want all the continuous functions. This is enough if you don't care about uniform limits, and I won't care about uniform limits. I will talk about later. And they also have other properties that I will get to it. What are my quantifiers? I can take supremum and infimum. The way I think about it, you could make different decisions here. I generally think of a formula being 0 as it being true. So the distance between x and y is 0 if it is true. And that means that generally infimum will act as an existential and supremum will act as a universal.
I understand this comment about Susan. Really?
Look, there are a lot of papers that will say that this is the max, that this is max, and also will say that 0 respect it should mean true. And then I get very confused when I start reading that paper. So there. And then we want to do the exact same thing. We want to allow countable disjuncts and conjuncts, but I'll give you an example later. If you take countably many formulas and you take their infimum, you're not guaranteed anything continuous. So we need to add this sort of rule for when you can take supremums and infimums. And it's essentially, hey, if I give you countably many formulas such that they all respect the same modulus and have the image in the same set, you can construct the supremum and the infimum. So if you're not breaking any rules, you can do it. This creates a problem in that I cannot just grab any countable collection and just make the supremum and infimum, I have to kind of go through this check. And that will be one of the technicalities I might get to, might not. Yeah, I'll get to. Okay, so examples again. Suppose I have a binary predicate, P. Consider the formula supremum over x and y of pxy minus pyx. Well, that's kind of telling you how symmetric P is. If the formula is 0, P is symmetric. Well, assuming P has range from 0 to something positive. Let's P doesn't output negative values because otherwise weird things can happen. And it's 0 exactly when P is symmetric. Okay, suppose I have countably many constants. Consider the supremum over x of this countable infimum of the distance between x and these constants. So that's exactly telling you how close the constants are to be in a dense set. If that formula is 0, then everybody is as close as you want to some of the constants. If not, it's telling you sort of by how much do you fail to be dense. And this is kind of the reason sometimes to do continuous logic is you have not only true or false, but you have a sort of degrees of failure. Now you have to interpret that somehow, right? For different formulas that might mean different things, but that's kind of the idea. And the last thing I kind of promised you, if I take countably many formulas and I take their supremum, I might not end up with something continuous. Suppose I'm in a Banach space. Consider this formula, the minimum of n times the norm and 1. If I apply that to any point and take the supremum over n, if I apply that to any point that isn't the origin, well, at some point that's going to be 1. So it's 1 everywhere, but 0 at the origin, not continuous. So this extra rule we put in, we really do need to put in. Okay, let me talk about connectives. If you've seen continuous logic before, again, sometimes you might want to add some authors add all continuous functions. Why do I want my set of connectives? I want countable many. Okay, that's cool. But the real reason is the third one. The second thing that I want to convince you of is I don't lose any expressive power. By Stone-Weierstrass, really the lattice version of Stone-Weierstrass. If I have a function from some product of compact intervals into a compact interval, it is the uniform limit of the connectives I've just made. So if you want any connective that you could think of, you can write it as a uniform limit. And really the reason why I want to use these connectives is that I get nice pre-next normal forms. This doesn't happen necessarily. In fact, it doesn't happen if you have multiplication. If you have a formula that's a supremum times another formula, if that formula takes negative values, for the negative stuff you have to do an infimum, and so you end up with this supremum of infimum, and you increase the quantifier complexity if you want to put it into a pre-next normal form. And because I want to talk about pre-next normal forms, so I can do quantifier complexity, I need to stay.
Can't you, I mean, you know what, range of psi, maybe you're talking nonsense, but I'll talk.
Yes.
So a range of psi is a bounded interval.
Yes.
You can just add something big enough so that it's positive, take supremum and then just subtract it back.
Sure, that works for multiplication, or in this case.
Yes.
Now, for every continuous function you can think of,
Yeah, yeah, okay.
what is the yes?
I'm just
It
saying
is
it's not a
salvageable.
good example.
Yeah.
Okay.
But again, the problem is if you want to use any continuous function, that you have to come up with the process. So
But still,
want-
it's going to be bounded, so you can always
Yeah.
push it up and that's right. Add, subtract.
yes, that works here.
Okay.
So okay, I have put in for the connectives I have talked about max, min, plus. I hope I can convince you that that you can just pull out the quantifiers. The only asterisk is if you multiply by a negative quantifier, you have to flip it, which same thing you do in classical logic. So okay, I can tell you what an inf alpha formula is now. It's the same idea. It's inf alpha if I can write it as a countable infimum of some infimum over some number of tuples of some formulas all of which are sub beta for some beta less than alpha. So essentially the same ideas here, except this is now a countable inf, and this is an inf over some tuple. And again, I'm only counting the quantifier alternations. But this leaves, yes.
Come with the restriction from.
Oh, yes.
The delta
Right.
should also appear.
So yes, I guess what we're saying is that all of these formulas here satisfy some modulus.
Yeah.
So I know where the modulus is. I'm saying if it's a valid formula, here's how you calculate its complexity. But this sort of leaves up the question of what do we do with uniform limits? Because again, you don't have full expressive power with just the formulas because I don't have all of the functions. And in fact, even if you add all the functions, you still want for certain reasons to be closed under uniform limits. So let me talk about the way that one of the ways in which you close by uniform limits, which is called definable predicates, which I hate the name because they're neither definable nor predicates. Because if you remember, for me, the way that I presented this, a predicate is just the basic relation in the language that goes from some Cartesian product of the model to the reals. These aren't that. So, okay, but what are they? If I give you a metric structure, a function from A to R is a definable predicate if it's the uniform limit of formulas. That's all they are. And I'm gonna also, so okay, why are they the right thing to think about?
Are you talking about infinitary formulas or about finitary formulas now?
Infinitary formulas.
Infinitary, okay.
Yes, if they're the uniform limit of perhaps infinitary formulas.
Not too many more letters in uniform limit of formulas than there is in finable predicate.
True.
What was that? What was the suggestion?
There's not too many more letters in uniform limit of formulas than there is.
I won't contest the point.
Twice as many words.
But why are they interesting? So one of the things that is true about formulas in classical logic is that the formulas are exactly the continuous functions from the type space to 0, 1. That's not true in continuous logic. In continuous logic, if you want the continuous functions from the type space to the reals, you need to actually consider uniform limits. And we're going to extend the notion of quantifier complexity to definable predicates by saying, hey, a definable predicate is inf alpha if it can be written as the uniform limit of inf alpha formulas. Okay? I just want to be able to describe quantifier complexities. This creates some interesting issues. Like if you consider the function p of x is pi times x, the reason why I want to think about the complexity of definable predicates is that pi is not a connective in my language. Remember, I can only quantify by rationals. So if you want the complexity of this as a formula, you have to do the supremum over all rationals less than pi of r times x. But as a definable predicate, this is quantifier free. I'm sort of like, I made these choices and now I have to live with them. Okay, let's go back to perhaps the biggest technical problem that we have, and it's this whole issue of, okay, I'm not close over countable supremums and countable infimums, and it's really hard to build a theory of how separable structures work if at every stage when you give me a countable collection of formulas, I have to like decide whether the supremum or the infimum is whether I can take the superinf. There's also this other weird thing, which I don't have the time to maybe fully explain, but for reasons that will hopefully become, well, for historical reasons, if you've seen the work of Scott and you try to sort of build it into continuous logic, you'll often end up sort of wanting to think about this quantity. If you give me two tuples, how much do they differ amongst all the formulas? Well, the problem is that quantity is either 0 or infinity, because they either always agree, or if they disagree on some formula by epsilon, well, then 2 times that formula, 3 times that formula, 1,000,000 times that formula is also a formula. And so this isn't really a continuous measure. And I'm doing continuous logic. I want a continuous measure. So what are,
measure? Don't see why is this measure at all?
well,
In what
I'm using
sense?
the word measure as an idea of how different the points are. I'm not saying it's actually a measure in the mathematics.
Is that called metric?
Sure, sure. I guess the right word to put there is it's not a continuous metric. Fair enough.
It's gonna satisfy Rayo?
Yeah, the way the R alphas that Ben-Yakov's builds are pseudometrics. But you have to use this trick. So again, if I do all the formulas, it's either 0 or infinity. So I need a way, I want to fix this to problems. I want to always be able to take countable subs and countable limbs, and I want this quantity or some version of that quantity that is actually, I guess, just to satisfy Elias, a metric. So what am I going to do?
Okay, right. I always forget that sort of. I never take advantage of that.
So essentially the idea that Ben-Yakov et al. Come up with is I'm going to put a different speed limit for formulas of different array. So this is what this weak modulus of continuity is. It is a function from 0 to infinity open up to n, all the way up to 0 infinity closed, that is still a modulus of continuity. So it satisfies these nice properties. It's continuous on every variable, and it's lower semi-continuous in the product topology. There is some idea here. But really, what I'm thinking about is I'm making countably many modules of continuity and sort of putting them together. So for unary formulas, I'm going to say that your modulus is just the one for the first entry. I guess infinitely many zeros. Binary formulas get the modules that you get from the first 2 entries, so on and so forth. And basically the idea is I'm going to have those modules sort of increase. So one way that you can do this, if your language is Lipschitz, every symbol has a Lipschitz constant, I can say, okay, unary formulas, your Lipschitz constant has to be 1. Binaries, it has to be 2. Ternaries, it has to be 3. So as you increase the number of variables your formula takes, you're allowed to grow faster and faster and faster. And in fact, it turns out that if you have a collection of formulas, well, they all satisfy omega, then you can just put subs and ints together. The problem is, why haven't I lost expressive power, right? I mean, there might be a unary function that grows with Lipschitz constant 3. Didn't I lose it in the way? So the extra restriction that Ben-Yakov et al. Add essentially is this. Omega is universal for a language L if for every atomic formula phi, let's say, of x1 up through xn, and every m greater than 0, this is a real number, there is a k such that the formula psi on n plus k variables, which is really m times the formula phi on the last k. Sorry, k plus 1. Sorry, in the last n. Let me just say k plus n so it's more clear. is an omega formula. So if you give me an atomic formula, it's not necessarily an omega formula, but if you sort of add a bunch of dummy variables at the beginning, then it will become an omega formula, even if you allow yourself to multiply by arbitrary large numbers. And it will turn out that this is sort of the right definition to get a collection of formulas that still has enough expressive power, but where I no longer have these, I need to look at continue supremums and infimums. And actually, if you take these expression, the supremum over all formulas phi, and you say, okay, I'm only going to look at the formulas phi that are omega formulas, then that is actually a pseudometric on the structure, and it's actually a pseudometric capable of classifying the structure up to isomorphism. I don't know if I have time to talk about all of that, but it turns out that this is sort of the right definition to do this kind of Scott analysis. Oh yeah, I didn't say a formula is an omega formula if it satisfies omega as a modulus of continuity. Ben-Yakov et al. Use a more restrictive definition where they say you're an omega formula if you're built out of omega formulas in a sort of, you need to sort of be built out of omega formulas. So why is that different? Let me explain. Perhaps this is this might, no, I don't know if I'll have time to come up with that, but consider something like this. I have a formula phi. And let's consider the formula in, okay. I will return to this question of why is my definition different from Ben-Yakov's eventually. I need to introduce some other stuff. But just keep in mind, okay, what's an omega formula? A formula that satisfies these universal modules of continuity. Okay. Right, this is just what I just said. Okay, let's talk about definability in continuous logic. Definability is actually weird in continuous logic. If you were to sort of do the analogy thing and bring definability from classical logic, you could come up with a naive definition that says a set is definable if it is if there is a formula so that my set is exactly the points where this formula takes the value, say 0. Turns out that this is too weak of a definition. In particular, you can't use it to quantify over that. Just because a set is, this definition is called zero set definability. Just because a set is zero set definable, it actually doesn't mean that that if you give me a formula, the infimum over all things in my set with the matrix is actually a formula. That turns out to be too weak. So what notion of definability we're gonna come up with? It's essentially the sets that I can write down the distance to that set. And what distance? Because you could do it for any metric on your structure, because we really want to talk about our omega formulas. Turns out that these modules of continuity gives me a metric on an for every n, where the distance between two tuples is just omega applied to the individual distances. So I have this distance on each power of a, and I'm going to say that a non-empty metric closed subset of A is definable if there is a definable predicate that's exactly the distance to that set.
Decoding.
Yes.
The distance to this set is a uniform limit
Of formulas.
formulas.
Yes.
Okay.
Yes, you have everything is closed under uniform limits. And okay, maybe today, I don't know if today I have time to give you all the examples, but there is actually a difference between this sort of notion of a set being the points where some formula takes a particular value and the distance to that set being definable. Interestingly, if you think about it in classical logic, they both collapse to the usual notion of definability because the discrete metric is just very nice. So this is a case, this is perhaps the one place where the analogy thing actually has some choices and it's a little bit more complicated. Why does the set have to be metrically closed? Well, this is going to give me a closed subset. So I can only define metrically closed stuff. I don't know if I have any more things. Any questions about definability? Yes.
If you want to deal with this at the end rather than, since you asked. So I've been talking about definability in LMA and Omega with Jose Opino.
Yeah.
And he says the proper definition is that uniformly approximable compact sets via polynomials. And he claims that this is, if you go to Kiesler's original book on L omega and omega, that's a translation of what he has. Just sort of.
Okay, I will say I am not aware of it. Okay, so you said uniformly approximable in compact sets by polynomials. Okay, so uniformly approximable by polynomials is just the same thing as definable predicate, right? Because, well, I added all the polynomials. On compact sets.
Let's talk about that.
Yeah, it's weird because compact sets are sort of the continuous analog of finite sets. And so it sort of, this definition feels weird to me. I would have to read more about it before I can say anything. Now, you can easily show that this definition is equivalent to the set being quantifiable. So if you give me any predicate, I can build the infimum over all points in this set, the supreme over all points in this set. And it's also equivalent to a nice sort of continuity property of like for every epsilon greater than 0. So sorry, there is a definable predicate. Just to use a different letter, I'm going to call it Q of X, such that for every epsilon greater than 0, there is a delta greater than 0, such that if Q of X is less than delta, then the omega distance of X to this set is less than epsilon. So if you can sort of, if my predicate sort of is able to tell you when you're close to that set, then you can actually build a predicate that is actually the distance to the set. However, going from this to this involves using as a connective an arbitrary increasing continuous function. And in Ben-Jacob's definition, it's not clear to me how that's allowed, which is why I just say you're an omega formula if you satisfy omega. If you're ever interested into the technicalities that are here, come talk to me because I don't know if many of you are. Maybe Elias is, but I don't know if I grab. But again, anyways, I have a notion of definability. And so now kind of what I want to say is that, well, the first sort of punchline that I had at the beginning, that for any tuple, the automorphism orbit, or rather its metric closure, is definable. So given any point, I can tell you how close you are to some image of A by automorphism. So how do we get there? Well, we need to look for isomorphisms. So how can we sort of build isomorphisms of a separable metric structure? Again, we go by analogy. If I give you a countable structure, how do you build a bijection or, yeah.
Just, I
Yeah.
just,
Yeah.
so you use automorphisms and look at an end tuple and look at how close it gets to. But what happens if you didn't do this and just did the natural thing, which is looked whether you could actually go to the zero set?
So the problem with the zero set is that, okay, so the formula for the zero set, right, is just going to tell you, correctly the elements that are in the zero set, right? It's not, if the elements that aren't on the zero set, the formula is just going to say something, but that something doesn't mean anything. That's kind of the difference between zero set definability and definability, right? If the formula is 0, you are an image of that of A. But if the formula is a half, what does that mean? That is kind of the difference. When you have full definability, well, you know that the closest image, the closest automorphism image of A to U is a half away. And if you look at this equivalent definition, definability is exactly saying that, hey, if the value is small, then you're close to an automorphism image. So if you're not definable, even when the value is very small, you could be very far away from the automorphism image.
Another thing that one could say is that you want your definable set to survive ultra powers. You want
Yes.
closest theorem.
I see.
And unless you do this.
Yes.
just-
So maybe, yeah, I guess the reason why I haven't gone there is because I'm only working with separable structures. But yes, the definable sets that are exactly the ones that survive ultra powers, or even ultra.
Elementary sum
Yeah.
models. I mean,
Yeah.
you work with elementary sum models.
Yes. Okay. So does that kind of make sense? Any other questions? Okay. So now we want to look for isomorphisms. Okay, let's do analogy. I have a countable structure and I want to build an elementary bijection. What is the most classical way to do it? Say if it's Q. You go back and forth. So we want to do some kind of back and forth. The problem is we're separable, and what does that mean? So you have to decode it, and it turns out to be a little bit more annoying, but I'm going to give you sort of the general framework. Suppose I have two separable metric spaces. I'm going to fix countable dense subsequences. So I'm going to fix a countable dense set. I'm going to order those into a sequence, but I'm going to be careful in that I want the tail of each sequence to also be dense. So if you kick out Feynman stuff, you're still dense. This is equivalent to the sequence being dense and every isolated point appearing infinitely often. Okay, I just want to make sure that if I've used finite amount of stuff, what I have left is still dense.
Sorry, okay, you're
Yeah.
just doing a back and forth, but back and forth doesn't give you isometries. It just gives you.
We'll get there.
Okay.
So we have to be very careful about how we do this back and forth. Okay, and that's the question. Okay, so if I have these two dense subsequences, what information about them extends to an isometry or an isomorphism, really, of the whole thing? So remember, omega here is a universal modulus of continuity. This is important. An omega bounded back and forth set with bound t greater than 0. So there is a bound here that is going to be t. Think of it as like the maxed amount of error that I'm going to tolerate throughout this process. So I'm going to build a back and forth sequence, and I'm required to allow some error. One way to see it is take the rationals in the unit interval and the rationals in the unit interval and add an irrational number, let's say pi over 5. If I want to build a back and forth set, at some point I have to go to pi over 5, and that's going to build some amount of error because the distances here are always rational, and here I'm going to have irrational distances. But these two structures are isomorphic, so I have to allow some amount of error. It's just that I'm not going to allow infinite amount of error. I'm just going to allow t amount of error. Between these test subsequences is going to be a set with the following properties. If you have a tuple from A and a tuple from B in my set, then the max amount of error, right, this primum over all formulas of okay, evaluated at A, evaluated at B, take the difference, is less than t, where phi of x varies over all quantifier-free, all omega quantifier-free formulas. Okay, to be fair, I want to say that I is really, if you press me for it, I is really a subset of the union over n less than omega of A to the n cross B to the n. So I only have tuples of the same length. So this is kind of saying they have the same quantifier free type, but I need to, again, if we used all formulas, this value is either 0 or infinity. So we're restricting to only the omega formulas that have shown up yet. And remember, as the arity increases, I become more permissive. So my first choice is actually the most permissive choice. As I build my sequences, as the sequences increase, I have to make better and better choices. And I have extension properties. So if a pair AB is in my set, then for every C in A, I can find a D in B, such that AC and BD, AC comma BD is in my set. So I can extend on one side, I can extend on the other, and I have this weird condition that the index of the thing I'm adding on the other side. So for any C, I can find a D whose index is larger than all the indices that haven't appeared before, and I can extend. You don't need that, but if you've done any kind of computability theory, you know that using fresh new constants makes a lot of proofs easier. So this is just here to make a lot of my proofs easier. And this is fine because remember that my sequences are tail dense. So I can keep going to the right without paying a penalty. And this turns out to be exactly what I need for isomorphism. So this is the theorem. Take two separable metric structures, omega universe of modulus, fix any bound T you want, pick countable tail-dense sequences. If there is a bounded back and forth set with bound T, such that A and B are in I, then I can actually find an isomorphism such that the image of A is no more than T away from B. So notice I cannot even guarantee, it's not, because T has to be greater than 0, I cannot guarantee that A goes to B, but it doesn't go too far away.
So the F here is the phi, right?
Oh yes, I fixed this last night and I made that mistake. Yes, this should be a phi. Thank you. So this is kind of the right way to build back and forth sets. And just to give you an idea of how you do it, you first pass through the game that you would normally play. So we're gonna play a game. The objective of this game is to build two increasing functions from omega to omega. I'll show you what we're gonna do. And I have really the A side and the B side. And this is what we're gonna do. First we play A0. The extension axiom tells you that there is some B with some index here, such that A0 BK is in my set. I'm gonna call this F of 0. Then I'm going to play B0. And again, extension tells me, hey, there is some AG0, such that A0, AG0, BF0, B0 is in my set. And I keep going on. And then what's gonna be true at the end is that I'm gonna build my isomorphism as follows. I'm gonna say that phi of A is B if there is an increasing function, let's call it I, from omega to omega, such that on the A side, A is the limit of over n of AI of n. So if I select only the subsequence that I select, on the A side I get A, and on the B side, well, notice the translation. B is going to be the limit as n goes to infinity of B I of f of n. So notice that even if A and BF0 are put together at the beginning, this doesn't guarantee that phi of A0 will be B of f of 0. because I really care about what's happening at the limit, right? Again, this is because my first selection is the most permissive. It's what's happening as I go off to infinity that I really care about.
Isn't it F of I of N?
It's whichever one it should be.
It's F of I of N.
Okay.
Actually, yes.
Yeah. Okay, so this is kind of how I'm gonna build isomorphisms. And with that and some other, so first of all, this is a theorem from the Ben-Jacob et al. If you fix a universal modulus and you pick any two tuples in them, B is in the closure of the automorphism orbit of A, if and only if they agree in all the omega formula. So really, this family omega is as dense as it should be. And then you can sort of do the trick of saying, hey, what would be a nice back and forth set is the pairs AB such that A and B agree on all the omega formulas. You pull that into your back and forth set and you realize, oh, B cannot be too farther away from A. And so using all of this machinery, we can actually get to a definition. That for any tuple, there is actually a formula that gives me the distance to the automorphism orbit. And okay, once you have the distances to all the tuples, then you can do any definable set because definable sets are automorphism invariant. So it's really the union of all of the automorphism orbit, all the orbits that are inside the set. So you can define anything you want. This is interesting. It tells us that continuous infinitary logic is kind of is maximally expressive for separable metric structures. And it also gives us a sort of this robust definition of Scott rank following Antonio. So I'm going to say that the Scott rank of a separable metric structure is the least ordinal alpha, such that for every tuple, I can define the automorphism orbit using an if alpha formula, or actually definable predicate. I might need to take uniform limits. The remaining question is, do I get this nice theorem of Antonio? So if you remember, Antonio's very nice theorem was the Scott rank is the least ordinal alpha such that you can define every single tuple by a sigma alpha formula. The Scott sentence is pi alpha plus 1, and you have these isolation statements such that every pi alpha type is sigma alpha isolated. So the question is, does the same thing happen here? So it turns out that the first and the third condition are easy to be shown equivalent. If you can define all the orbits, then if all the orbits are sigma alpha definable, are inf alpha definable, then every sub alpha type of definable predicates is inf alpha isolated by a definable predicate. If I have time, and I probably won't, I'll tell you what isolation means, because it actually is a little bit weird. So I guess I'll throw out this comment, something that Ilias learned in a paper of him and Magidor is that omitting types in continuous logic is weird. But these two are the same. So we have equivalence between 1 and 3, and they actually both imply 2. If all the orbits are inf alpha definable, then I can easily build a sub alpha plus 1 Scott sentence. The Scott sentence, what does the Scott sentence essentially say? It essentially says that you can build a back and forth set. The sentence kind of gives you the blueprints to make the back and forth property work. But the question is whether you can make 2 imply each of the other 2. So if you do have a pi alpha plus 1 Scott sentence, can you get either that all the types are isolated or that the all the tuples have definable orbits? That's kind of where I stumbled, because that requires a type omitting theorem, and I managed to get it. I guess I didn't say here. Because I am very close to being done, or when I made these slides, I capped it off here. But let me just quickly go to a place where that happens. Hi. I can get the type omitting theorem at limit ordinals. So what does this type omitting theorem say? I will, I don't have time to give you everything, but essentially, if you have a sub-alpha formula, a sub-alpha formula for some limit ordinal alpha, and a sub less than alpha type. So this type it has formula sub beta for beta less than alpha. Then you can build a separable structure that realizes the formula and omits the type. But I can only do it for limit ordinals, because there's a weird spot where I have to increase the complexity by 1. And I have not managed to figure out if you can sort of fix that.
So I don't
Yes.
understand, Trish. So here this psi of x is omega comma sup less than alpha minus type of a.
Sorry,
What does
that is a dash. It's an
dash.
This is a dash. So I didn't go through the entire definition, but
Okay.
it's all the omega formulas whose complexity is sub less than alpha. So is sub beta for some beta less than alpha that are true of A.
Uh-huh.
That is what I mean.
So it's restricted type of alpha.
Yes.
Just
Just
but
thought it
you
out
have
at this.
a free type, but you're
Yes.
going way higher.
I'm going way high. I'm going up to. I need to go up to some limit ordinal.
So I'm just
Omit means nobody realizes the type. So notice, so this is a type omitting theorem, right? I have this formula, this structure A that thinks Q is true and realizes this type, because this is the type of a tuple. And what I'm telling you is I can build another structure B that also thinks the formula is true, but omits the type. In particular, A and B are not isomorphic, because there's no way you can send little a. In particular, Q is not the Scott sentence, because it thinks it's true, but they're not isomorphic. So what this statement is really allowing you to do is to show that certain sentences are not the Scott sentence. The problem is I can only do it for sentences that have this weird limit ordinal complexity.
But did you define this omega comma inf less than alpha supported? Because
Oh, yeah.
But,
So
if you did, I forgot. So I'm
yes, so essentially which is not supported. Okay, so what does supported mean? Supported means is that a type is supported if there is a predicate, which is 0 somewhere, infimum 0, and essentially it's supposed to be close to what happened in the classical case, which is if the predicate is true, then the type is true, but you have to say it approximately. So what we're going to say is that if the predicate is less than epsilon, then the type is approximately true. And the way that we define approximately true is using these weird distance on types. Essentially, if the predicate is less than epsilon, you are close to a realization of the type approximately.
but is that the usual thing? That the distance is the infimum of distance as in some saturated model.
Yes, but again, in infinitary logic, you cannot. It doesn't quite work like that. However, there is this actual definition by a formula. However, notice there is an additional quantifier here. This additional quantifier is the root of all evil for what I'm trying to do.
Why do you need exponent q?
This just means that this thing evaluated at q is 0.
Or at Q.
Yeah, it's just that in infinitary logic, for some reason, you don't use the model thing. Instead, you do that. I don't know if I have time to do that because I have 15 minutes left. So let me just go back and give you kind of the generic end to the story. As if I give you a separable metric structure, continuous logic can define the metric closure of each automorphism orbit. You can put those together to get Scott sentences, and you do get this nice. You start to get this nice robust notion of Scott rank. If all the automorphism orbits are inf alpha definable, then all sub alpha types that are realized are inf alpha isolated, and those two are equivalent. They both imply that you have a sub alpha plus one Scott sentence, but we're missing kind of that one direction to get the nice equivalence from Montalban. And again, the reasons are type omitting is weird. For today, I think that's all you need to know. Here are references. And I will say thank you for right now and take questions so we don't go super over time. Are there, okay, okay, let me first do questions. Are there any questions before I go into the type omitting stuff? Or should I just do type omitting for 12 minutes and see where we end up? Okay, let's do type omitting for 12 minutes and see where we end up. Okay, so we want to talk about types. But again, if you remember before, we wanted to talk about pi alpha types, sub alpha types. So, Elias put it well. You want to think about not the quantifier free type, not the existential type, but, give yourself any amount of quantifier complexity. And so we can define those types. So the omega sub alpha type of A, well, you could write it if you want as the set of all sub alpha formulas that are 0 at A. For reasons here, I actually write it as the set of pairs sigma R such that, phi R such that phi at A is less than or equal to R. Now that's for formulas. You can also do it for predicates, aka close under uniform limits. So that is where the weird bar on top of the sub alpha means. It means I'm not just talking about formulas, but I'm talking about definable predicates. And when I have a limit ordinal, I can put all of them together, but not cap it off. So for example, you can think about the sub omega type. That would include formulas that are sub omega. So the supremum over formulas that are sub n for some n. Or I can just not have those up. So the omega sub less than alpha type of A is the set of all predicates that are sub beta for beta less than alpha and are 0 at A. These are kind of, essentially, these are the types that I can hope to omit. I was not able to omit every type, but I was able to omit these types.
You mean that complexity is bounded in a given type?
Yes.
So if it blows up, then you have a. Okay. That
Yeah.
sounds.
So you can actually hope to omit, say, complete types. The problem is the lack of the incompleteness makes them harder to think about. Okay, so let me talk a little bit about types in continuous logic. So if you don't know this, well, here's a quick introduction. If you look at the space of types of a theory in continuous infinitary logic, it's what's called a topometric space. You still have the good old logic topology, where the basic sets are sets of the form, a formula phi is less than R. But you can also put a metric on it. And the two do not necessarily agree. What is the metric on the types? Well, if you are not doing infinitary logic, if you're just doing continuous logic, you can say it's the infimum of the distance, or the infimum amongst all realizations in some model. So it's the infimum of the distance between A and B, where A realizes P and B realizes Q. If you go to infinitary logic, you'll lose the compactness theorem. So you can no longer do that. But you can do that approximately. Or as this is, I think, by I think I want to say this is Benyak. No, I forgot right now where this result comes from, but we can create this distance between types P and Q, where we say the distance between P and Q is less than S, if for every formula, I cannot do all types, all formulas. I'm gonna pick a fragment. A fragment is closed under, did I say what it is?
Yes.
Yes.
Is it, what about the?
Quantifiers, subformulas, sub and countable sub and countable length.
Countable element is one.
Yes. For every formula, Q thinks, let me make this into first order logic, that there is approximately a Y whose distance between X is less than S, and Y basically realizes P. So it's essentially saying approximately every realization of Q is no further than S away from a realization of P. But we're only doing this formula by formula. We're not doing it the whole type all at once. Okay? Do note, and here's the problem. Suppose that your type is sub alpha, right? So phi might be a sub alpha formula. This formula here is now inf alpha plus 1. So saying you're not too far away from a realization of P involves an increase in complexity. And this is something new to the infinitary setting. In the classical case, you don't have to deal with this. And I'm going to call theta of phi, P of phi, and S this in this big formula inside the brackets. So there's this old theorem, well, not all, about a decade-old theorem of Eagle that says, hey, take a separable fragment, so of continuous infinitary logic, a consistent theory, and some set that is meager in the logic topology, but open in the metric topology. So small according to the logic topology, big according to the metric topology. Then there is a separable set of types. Then you can build a model that omits those types. This is essentially, and the upshot here to me, if you remember your type omitting theorem, in classical logic, you can omit meager sets of types. The new restriction here is that they have to be open. So in particular, if you want to omit just a particular type, you have to omit some open ball around that type. So it's not enough to just omit the type, you kind of have to omit all of the types that are somewhat close to it. And if you want me to give you a reasoning, or one possible reasoning, is if you try to do the Hankin construction to omit the types, well, your Hankin construction is really just gonna build a countable dense subset. And so you can only make sure that the countable dense subset omits the types, but okay, maybe you start getting close, and the moment you close your countable dense subset to get a whole metric structure, you realize the type. So essentially, you need to make sure that all the Hankin constants stay away by some epsilon from the type you're trying to omit. So type omitting in continuous logic is harder. It involves a sort of new idea. Okay, this is this sort of notion of isolation that I have, which is similar to supported. So let's again fix a weak modulus, an alpha greater than 0, a partial type. So what I mean by a gamma L type is, I mean an omega L type is a type of omega formulas with any complexity. I'm just not putting any complexity values. Is supported in A if there is a definable predicate with minimum 0, such that A believes that there is approximately a realization of P. So if you want to go back to Antonio's definition, there exists an X such that A believes P of X. And I'm just gonna say it and then we're gonna talk about it. For every epsilon greater than 0 and every tuple, if P of X is less than epsilon, then that horrible formula we saw earlier is 0 for every formula. So let me remind you what this formula says. This formula says that there is approximately a realization of there is no more than S away something that according to this formula agrees with P. So if we go back here, you're saying if this predicate is less than epsilon for any formula in my type, no more than S away, you can find somebody who agrees on that formula with what P says. So approximately, formula by formula, you have a realization no more than S away. So it's kind of like telling you that you're close to the set of realizations of P, but because we don't have compactness, we have to do it formula by formula. So again, supported means there is this one predicate that is sort of capable of telling you are close to realization. Now let's go back. So if you remember, if a type is not isolated, it's omittable in classical logic. So we want a theorem that says something like that, that if a type is not supported, then I can omit it. But I cannot do it for a whole theory. This is an infinitary logical case. But what I would like to say is that for any formula, so what I would hope to say, the general theorems should say, for any ordinal alpha, if you give me a sub-alpha formula, which is realized in my model, and a sub-alpha type that is not inf alpha supported, then I can build another model that realizes the formula but omits the type. In particular, that is not the Scott sentence. I can't do it. I can only do it for limit ordinals. And essentially, why? Because I want to make a Henkin construction with inf alpha formulas. But in that Henkin construction, I want to say, hey, this Henkin constant is not close to a realization of P. But if you remember, then I will have to use this formula, which increases the complexity. So I have to go to inf alpha plus 1. And once I've done it once, I might have to do it again. So I have to go to inf alpha plus 2 and inf alpha plus 3. So the only place where I can do it is if I am below a limit ordinal where I can add 1 however many times I want and not go up. So that is kind of the technical difficulty. There might be a way to surpass this. I don't know. I wasn't able to figure it out. But that is kind of the reason why I can only give you these equivalents at limit stages. Hopefully my rambling made sense, because at this point I'm kind of deep into the technicalities.
Actually,
Yes.
what does B have to do with alpha? I don't see alpha just disappears at some point. Why does?
So remember, the formula that I'm trying to omit is sub alpha.
Oh, it's
the formula I'm trying to keep true is sub alpha, and the type I'm trying to omit is sub less than alpha. And I'm just saying I can put that together into a model. Yeah. Any other questions? Anyways, I will close then by saying it remains open the question whether this theorem is true for all alphas. I keep going back and forth because this theorem not being true has some very weird consequences about the complexities of structures. But I also haven't found a way to do it, nor do I have a counterexample. If you are interested in working in this area, hey, there's a hard problem I don't know how to solve. Go for it.
Check it for small ordinals. And what is the first alpha for which you don't know?
Well, the problem is once you start, the problem is to get into a problem, you kind of have to find a structure of very low complexity for whom a type is not isolated.
Right.
And if you think about a very nice structure that you very well understand, they all work out. So you have to sort of come up with some weird structure of low complexity.
Oh, yeah.
And that is, yeah. Anyways, thank you very much.